Welcome to this video, guys. This time we're going to talk about Bayes' theorem. Let me show you real quickly how we can come up with the Bayes' theorem. Well, first of all, as almost always, we're going to begin with the conditional probability. If we use the definition, we know that it's the intersection over the probability of the given event. Of course, we need the probability of B to be greater than 0. So now, how about if we solve for the probability of the intersection? Then we're going to have the probability of the intersection is going to be the probability of A given B times the probability of B. But that's not the only way in which we can find an equal expression for the probability of the intersection. Here we use P of A given B. We can write also, let me switch colors, we can write it P of B given A. Of course, these are P of B given A is not the same as A given B, but we can work with this piece using the definition B intersection with A over probability of the given. But now we know, let me write it over here, that the intersection of A and B is the same as the intersection of B and A. So this probability becomes the probability of the intersection of A and B over the probability of A. So now let me erase this middle part. Let me write here equals, and let me move this over here. So that's it. So we have two different expressions. So let me solve again for the probability of the intersection. Sorry, guys. This is just P of B given A times P of A. Okay, so now we have two different expressions for the probability of the intersection. So of course this is the same as this, therefore this must be the same as this. So let me write that in a new slide. Probability of B given A times the probability of A is the same as the probability of A given B times the probability of B. So now again let's solve for this, and we will have probability of A given B is going to be P of B given A. We're going to switch places, A given B, B given A, times probability of A over probability of B. And this, guys, is called the Bayes theorem. This little star equation is what's known for Bayes theorem. Of course, you already have, or hopefully you have, this intuitive idea that this is not the only way to define Bayes' theorem. We can do it the other way around. We just switch all the A's for B's and all the B's for A's, and it's the same thing. So these two expressions are the same. They are both the Bayes' theorem, and Bayes' theorem this just at this first glance give us a relationship between the two conditional probabilities, the P of A given B and the B given A. So we have a way to compute one conditional probability if we have the other, or the other way around. So this is the Bayes theorem. So let's work with one example. Let me make a drawing so we can save. I can spare you the writing. So let's make a diagram. Let's say that 20% of Campus Santa Fe students are sick around this time of the year. 20%. So if 20% are sick, that means that 80% are not sick, right? Let me write this as sick complement. So 20% are sick, 80% are not sick. So now we have, they are sick of some disease, any disease that you want. So we have a quick test to detect the ill students, and among the sick students, the test results will come up positive 90% of the times. So this means that there will be a 10% of students that are going to be sick, but their test is going to come up negative. And among the students who are not sick, who are sick complement, who are healthy, the test will come up positive 30% of the times. So this means that 70% of the times testing among healthy students, 70% of the times the test will be negative, but 30% of the healthy students will have a positive result. So after knowing this situation, what is the probability? Let's say that we randomly pick a student. The student takes the test, and the test comes positive. The results come positive. So the question is, what is the probability that selecting a random student and that student taking the test and the test coming out positive, what is the probability that the student is sick? Is actually sick? This is the question. So what this problem is really asking us for is for this. Let me write as the event of being sick, of the student being sick. Let me write this little plus sign as the event of the results being positive. Let me write as complement as the event of being healthy. So now we have, I believe we have everything to use Bayes theorem. So now that we have defined these events, this question in fact translates to this. What is the probability that the student is sick given that his test was positive? This is what the problem is asking us for. So let me copy the data, let me copy this diagram, and let me copy the question so we can work in a new slide. So there we go. Let me move this up here so we can work with it. So according to Bayes' theorem, this is going to be the probability of having a positive result given that we are sick times the probability of being sick over the probability of having a positive test. So most of the times, 99% of the times, when solving problems using Bayes' theorem, the hard part is not the numerator. Even though we have more terms than the denominator, most of the times the numerator is computed fairly easy. So let's focus on the denominator. Well, first of all, let's write the probability of having a positive result given that we are sick. Well, if we know that we are sick, that's the given event. We are in this branch of the diagram. So if we are here, what is the probability of having a positive result? Well, that is just 90%. The probability of being sick, well, that's very easy to find. It's 20%. So now we have the both terms in the numerator. Now let's focus on the denominator. Let me write it with white. So the probability of having a positive result is going to be computed using the law of total probability. So the law of total probability says that the probability of having a positive result is going to be the probability of having a positive result and being sick plus the probability of having a positive result and not being sick or being healthy. This is the first step. So now we use the multiplicative law to change these intersections into products. So the probability of having a positive result, let me write here equals and here equals, is going to be the probability of having a positive result given that we are sick times the probability of being sick. These two terms correspond to this first term plus the probability of having a positive result given that we are not sick times the probability of not being sick times the probability of being healthy. All these probabilities now written in this way are very easy to compute. So the probability of having a positive result given that we are sick is 90%, again equals 90% times the probability of being sick, which is 0.2. Look, this first part of the equation is exactly the same as the numerator, but we have something else, so it's not exactly the same. Now the probability of having a positive result given that we are not sick is just 30%. So let's write 30%. And the probability of being healthy, of not being sick, is just 80%. So let's write 80% or 0.8. And this is 0.18 plus 0.24, and this is 0.42. So 0.42 is the probability of having a positive result. So now we have everything to substitute in the blue equation in the Bayes law. So let me write it again. The probability of being sick given that we have a positive result is the probability of having a positive result given that we are sick times the probability of being sick. This is just this part, which is just this part, which in turns come up to be 0.18 over the probability of having a positive result. But the probability of having a positive result is this, which in turn is this, and this, and this, and this, 0.42. Let me write it. So now this is about 42.85%. So we have found that the probability of having the actual disease, given that we have a positive test, is less than 1/2, is less than 0.5. So again, I believe that this is a very counterintuitive example, since 90% of the times among the students that are sick, the test comes up positive. It looks like a very high figure, but the prevalence of this illness is not that high, so it's like a trade-off. So that's why we have a very low probability here. So finally, to conclude, Bayes' theorem tells us how we should adjust our belief in an event. For example, before we knew the result of the test, the probability of being sick is just 20%. But after we know that the test is positive, we have to switch from 20% to 42%, more than twice as much as the original probability. So that's one very useful thing that Bayes' theorem helps us with. And well, that's it, guys. Thank you, and see you later.